Good morning, class. Welcome to the online classes for class 12 physics. Here we have seen the chapter that is moving charges and magnetism in the last few sessions. So in today's class we will be seeing some MCQ patterns and how the answers used to be done. See the questions like the magnetic field due to a current element is independent of, right? So magnetic field of a current due to that element is given by dl, right? The current element is given by dl, and we know that the magnetic field depends on the current element. How, which formula is given by? It is given with the help of the Biot-Savart law, that is mu naught upon 4 pi I dl sin theta upon r square, or ideal cross r upon r cube. So what are the things that it depends on? It depends on the length, that is dl also, it depends on r also, it depends on current also. So I dl r together the three are depend. So the answer will be that it does not, none of this, that is it does not depend on any of the content that's given here. The second one, that is unit of current element is, the unit of current element, that is dl. dl can be given as, it is what it was given as, that is mu naught upon 4 pi I dl sin theta upon r square, right? So we know that I dl cross r upon r, so only r will be there. And if you find out for the elements current, then it depends on the current and its distance between them. So it is given as IR. So that is m meter into meter. So the answer will be m meter into meter. Similarly, see the next question, that the magnetic field be on the axis of a circular loop and a far away distance r from the center of the coil are related as. How can it be related as? Because if it is far away and circular loop was given like this, right, and it depends only on the cos thetas used to be cancelled and only depends on the sin theta. So we have written that the integration of the v sin theta will be given as the total magnetic field, and from there if you see that mu naught upon 4 pi 1, then 2 pi I a upon 4a. From there if you see that it only directly proportional to r inverse, no, because it does not depend on the r inverse. And similarly if you see r square, then it is directly proportional to r square, no. The third one is r cube. So we use this formula for the circular loop, right, and that too for the far away distance, that is x was excluded and we used to depend on the r itself. So the value depends only on the r, so it will be r cube. Now the next question, that is what happens to the magnetic field at the center of the circular current carrying coil if we double the radius of the coil having keeping the current. And a circular coil have some current, right, and if we take it on the double the radius, now the radius is double, then we can the diameter also increase, and we used to take the current at the axis point at center of the circular coil current. So on the circular coil current, if we take it on the center, then if the radius is doubled, then the current unchanged, by keeping the current unchanged, the magnetic field will be halved, because it does not depend on the size of the radius, but it depends that it is inversely proportional to the radius, because it is given as r square with the downwards, so it is taken as half. So the value will be halved. If radius is double, then the magnetic field will be halved. Okay. So the next thing, when we double the radius of the coil keeping the current rate unchanged, what happens to the magnetic field directed along its axis at far off points, right? It is given far off points, then again we have to use this is inversely proportional to r cube, and again it is given that if we double the radius, now the radius is doubled, then what the value will be? We know that the current depends on the r cube, the magnetic field depends on the r cube, and it is in the downward, so we get 1 upon r cube. Now if it is doubled, so what we can say, that the value will be cancelled since it is far away, so x will be cancelled and it depends only on the r. So it cannot be halved and doubled, but it will be quadrupled. Okay, so it will depend on quadrupled. Now the next question, the strength of the magnetic field around an infinite current carrying conductor is. That current carrying conductor is infinite, right? Infinite length depends on the current, that is 2 pi I upon a, then it inversely proportional to the distance, not directly, it is given as a at the down, that is inversely proportional to the distance. And next thing, the current power line carries current from west to east, and the direction of the magnetic field will be, and we know that the current flows from south to north, then it flows from east to west, that is the deflection is towards west, and now it is given that from west to east, so direction should be from north to south, so the option will be C, that is north to south. So the next one, That is, a metallic pipe carries a direct current. Which of the following statement is true about the existence of the magnetic field? So metallic pipe carries a direct current. So the field will exist only outside the pipe. It will be not inside the pipe, right? Because it's true about the existence of the magnetic field. Because inside the magnetic field there will be no, and so the metallic pipe only will have the current in the outside the pipe. Because inside the pipe there will be in the form of the coil. So the current will not be a direct one. So next question, the infinite straight current carrying conductor is bent into a circle. As shown, if the radius of the circle is r, then the magnetic field at the center of the coil is given by, we know this formula, right? Mu naught upon 4 pi, mu naught upon 2 pi, and given as pi plus 1 because it was mu naught upon pi I plus I, so it was given as mu naught upon 2 pi r pi plus 1. So its option will be D, that is mu naught upon 2 r pi I pi plus 1. The next question, that is, which of the following is not a unit of magnetic induction? So if the magnetic field is induced, then we can take any of the fields, that is Tesla is given at 10 to the power 4, it changes into Gauss, and Weber per meter square is also taken. So Oersted is not the unit of the magnetic induction. And next one, the magnetic field produced by a L meter long straight wire, then the current can hit any point on itself is, that is point here, since it depends only on the L meter strong wire, it depends on the strong long straight wire, and the current carrying conductor at any point on itself will be infinite, right? Because it will be infinite at any point. Now the next one, which of the following graph shows the variation of the magnetic field and the, sorry, there's no questions, here it is, that which of the following graph shows the variation of the magnetic field with the distance r for a long current carrying conductor. From here you can see which of this shows the long current carrying conductor, because it's inversely proportional and depends on the r square. So it will be C, the which is the inversely proportional or the changing one, that is the C, that is changing with the current. The magnetic field changes and depends on the distance between them. Now the 13th one, the magnetic field due to a current carrying toroidal cylinder does not depend on. Toroidal depends on the number of turns also, that is mu naught upon Ni. So it depends on number of turns also, current also, but it does not depend on radius. So it was mu naught upon Ni, so it does not depend on the radius. 14th, and what will the magnetic field in the empty space enclosed by the empty space, what it was, that is in the empty space the toroidal cylinder does not depend, right? Because by the in the turns which have the magnetic field turns, then only the current will show, so that it does not depend, so it will be 0. Now what is the magnetic field in the space outside the toroidal solution, then also it will be 0. It is only where the current is flowing or where the turns are there, only there itself the magnetic field will be. So here outside or inside the point it will be 0. Now next question, that the infinite long straight wire is bent into a semicircle radius. And then when current is I is sent through the magnetic field at the center of the semicircle is given by center of the semicircle. It will be 0 again. Now the next question, the charge Q is sent through a magnetic field. The force acting on it is maximum when the angle between the direction of the motion of the charged particle. We know that with this three, motion of the charge of the particle as well the force of the magnetic field should be maximum only if the angle between them is 90 degrees. They should be perpendicular to each other, so it will be 90 degrees. Next one, 1 Tesla is equals to that of Tesla means the magnetic field, so it is equals to the QVB, right? Force is equals to QVB, and from there if you find out the B's value, then it will be F upon QV. So we can write it as ammeter, that the current and the radius between them is at the downward. So the magnetic field can be given as Newton per ammeter per meter. So it is second one option. Now the no force acts on a charge sent through a magnetic field when the angle between its velocity and the magnetic field is, we know that no force acts. Since we have the 45 degree, then it will be half the 90 degree, 135 degree and 180 and will be 90, and we know that sine 180 will be 0. So not sent, right? No force acts on the charge, so we can say that it will be 180 degree. Next one, QVB, which of the following pairs can have any angle between them? Any angle between them. So what will be the angle between them? Then it will be F and V. It will be F and V. Okay. Next is SI unit of magnetic field is given as Tesla, and 1 Tesla is equals to the 10 to the power 4 Gauss. So this is the and the dimensional formula for the magnetic field is, what is the magnetic field? That's B is equals to QVB sin theta. If we take a force, and from there if we take out the value of B, we will be finding the value at F upon QB sin theta or QV. So it will be M T minus 2 and M meter inverse, because it is at the down, so it will be taken as M meter inverse. So the value will be D1, that is ML0 T to the power minus 2 and A inverse. Okay. See, which of the following is the unit of the magnetic dipole moment, right? M is taken as NIA, right? NIA. So the value will be area and current together we used to take now IA and IA used to take. N is the number of the turns and I and A are the current and the area. So area will be meter square and current will be A. So which option it will be? That is B, A meter inverse. And 26, see the next question, that choose only the scalar quantity. Which is the scalar quantity here? Magnetic dipole moment only depends on the current, so it will be area, so it will be depends on the vector quantity. Drift velocity is also a vector quantity. Then electric potential is the quantity which does not depend on the direction, so it only the does not follow the, we can say that it does not follow the vector quantities, it only follows the scalar law, so it will be a scalar quantity. Which of the following cannot be deflected while in motion by a magnetic field? Which does not deflect? So it will be neutrons, because they are neutral charge, so they will not be deflecting. Now the next question, that the force between the two parallel infinitely long conductor carrying currents in the same direction will be, since they are in the same direction, so there will be attraction. Okay. The force between the two parallel infinitely long conductors carrying current in the opposite direction, it is in the opposite direction, same direction will attract and the opposite direction will repel each other. The force on the charged particle in motion due to the magnetic field when the angle between direction of motion and the magnetic field is, so we know that they both together should be in the perpendicular direction, so the angle will be 90 degree. The dipole moment of the current loop does not depend on the, we know that dipole moment is given by the number of the turns also, area of the loop also, it depends on the NIA, so area, number of turns and the current. So the only word which does not depend on is magnetic field in which it is kept. Okay. So the next one, which of the following quantities of particle will not change when the charged particle move through a magnetic field directly perpendicular to its motion? Here the momentum is also changed, velocity is also changed. So what does not change? It is asked, will not change when a charged particle moves through a magnetic field directed perpendicular to its motion. So if it is perpendicular, then the motion or the speed will not change. Velocity will change, but speed will not. If its velocity changes, the momentum will also change. But speed doesn't, because it's a scalar quantity. What will be the nature of the path followed by the proton when it enters a magnetic field which its velocity parallel to that of the magnetic field? Now we know that the protons are positively charged and it enters into the magnetic field, but it is parallel to the magnetic field. So they will move in the straight line itself. So it will be option C. Now if we take the test charge Q enters a magnetic field B directed along the z-axis, the velocity of the test charge is V, and it makes an angle theta with B. Then what is the speed of the test charge after 2 seconds? After 2 seconds also, since it is in the z-axis, it will move with the same speed itself, that it will be B. Now the next question, that is, this dimension is given, what quantity, physical quantity it represents. We know that magnetic field is given by mt to the power minus 2 a to the power minus, that is, it will be the unit of the magnetic field itself. Now the second one, that is, if the mass of the charged particle is m and if it revolves, then angular speed is given with. Now if we take it as a charge q with directed along the z-axis and moving in the magnetic field B, then it will revolve with an angular velocity, right? So we know that force is equals to qvb sin theta. From there, if it take the mass as qvb and together it is taken as m, then what is the angular speed? That is, L is equals to p cross r, that is the momentum along with the distance. So what it will be, that qb upon m. So it will be qb upon m, and which equation it will be, that is the C1. So it will be QB upon M. So these are the kind of the conceptual questions for the magnetic field. But if you take it to the numericals also, there are some numericals, other numericals are also there. We will see in the next classes.